right? So if you can see on this plot over here, right, so what you can see over here is that the line is changing, right? So the red line wherein it would produce the least amount of error would be the optimum line. In this case, we can surely say that the one which is on the top side, that looks to be a reasonably better model than the one on the bottom side, because the errors you're creating is less in that case visually, right? But you need to actually see for this in your regression output itself. So what are we doing? We are basically trying to estimate the errors. So the yellow spot over here is the actual data. The aqua color is just the line which is intercepted on the regression line, and that is your predicted value. The gap between the yellow and the aqua point is nothing but your errors, right? And if it is more, that is harmful to you. So you're basically trying to do an optimization, which is a minimization function of the errors. So if the errors are less, that's the optimum line, and that's the concept of ordinary least squares. So specify the dependent and independent variables. So before you start off with your analysis, you should be sure as to what is your dependent variable and what is your independent variable. And nobody in this world is going to tell you what is the dependent and what is the independent variable. You have to check all these things yourself. With exposure to domain, you will understand that if you're working in an insurance domain, loss would be one aspect which would be of interest to business, and that is why you have to treat that as a dependent variable. And the other aspects as to which type of policy you have taken, the number of dependents, your disposable income, your job, whether you are self-earning or you are working in a company, all of these things would impact your dependent variable, and based on that they will create a big fancy model which you will obviously use in future to understand what is the loss which is anticipated from an individual, assuming he has these features in his data. So independent variables would be those variables which don't change often. Say for example, your age won't change, right? So if you look at a static data, your age won't change, your gender won't change, but your salary, which is usually taken as a dependent variable, is random. It can change, it can go up, it can go down. So it's not necessary that if your salary is at 10,000, it cannot come down to 8,000 or it cannot go to 12,000. That can change, right? So that would be independent variable, and all those things which are non-random would typically be classified into an independent variable, right? So when you're talking about, say, dependent variable is sales, revenue, element of marketing mix, product, price, promotion, place. Place obviously won't be part of dependent variable when you're looking at simple linear regression models. Obviously, if you're looking at logistic regression model, you can have a categorical variable also as y, right? So credit card application contains information about applicant age, marital status, annual salary, outstanding debts, credit rating. All of these could be a part of your independent variables. So now you're looking at an example of a fitting of regression model with the LM function. So how is this functionality used? So you just basically define a model name and then you use the allocation sign, and LM is nothing but linear model. You pass the formula and then the data, right? So that's how you write your equation. So wherein your formula is nothing but a y, that is the dependent variable, separated from the rest of the independent variable by a tilde sign, which usually comes on just next to your escape key on your keyboard, right? And if you do that, that is specifically telling R that take this as the dependent and take the other one as the independent variable. And also you need to pass the data into this algorithm. You don't need to think about what is the OLS and how the algorithm will work, because the LM function will take care of that. You will get an optimized model out of the same. And the formula is typically written as y tilde x1 plus x2 plus xk, depending upon the number of independent variables which you want to pass in the model. The tilde separates the response variable on the left from the predictor variable on the right. You might see quite often that we are using interchangeably some different names, like for example, you're using response variable sometimes, right? And sometimes you're using something like a dependent variable, right? And sometimes you might also call these as DV or IV. So DV stands for dependent and IV stands for independent variable. Now in your regression model, you will typically use some symbol. So tilde is the signage which is separating your x's from your y. So the left hand side of the tilde is your y, and anything which stands on the right hand side of the tilde is the x. If you just use the tilde and a dot, it means take all other variables except the variable on the left hand side of the tilde. The plus sign indicates that if you have to use more than two variables as independent variables, you have to separate them with the plus sign. That's how R will understand that these are part of the model. The colon sign denotes an interaction between predictor variables. So if you have multiple predictor variable and if you want to say that there exists an interaction between a variable. Say for example on your screen you can say y tilde x plus z plus x colon z. That indicates that there is some interaction effect between x and z and you want that to be part of your model. This asterisk sign shows that a shortcut for denoting all possible interactions. So the code y tilde x asterisk z asterisk w expands to y tilde x plus z plus w plus x colon z plus x colon w plus z colon w plus x colon z colon w, right? Something closer to a polynomial function. Now if you use a cap, it denotes interaction up to a specific degree. The code y tilde bracket x plus z plus w bracket close, right, and the inverted v and 2 expands to y tilde x plus z plus w plus x colon z, that's interaction, plus x colon w, that's interaction, and z colon w, that's again the interaction, right? So you can use it in this way also as a shortcut. Now if you want to use a placeholder for all variables in the data frame except the dependent variable, say for example you want to exclude some variable, right, then you can use a placeholder like a dot. Or if you want to include every variable, say y tilde dot, that would expand to y tilde x plus z plus w. If you want to remove something from this, you need to say y tilde dot minus w, that means it will remove only that variable, right? So a minus sign is used to remove a variable from the list, right? So an example is shown over here, y tilde x plus z plus w square minus x colon w, so that will remove those specific variables. A -1 suppresses the intercept. For example, if you want the intercept to be at 0, right, so that is called a scaling at 0, you can use a -1 also, right? So you can just say y tilde x -1, so it fixes a regression of y on x and forces the line through the origin at x is equal to 0. So you're saying the constant is 0 in this case. Now I bracket open close, that is in parenthesis, is the elements within the parenthesis are interpreted arithmetically. For example, y tilde x plus z plus w, z and w are in parenthesis and you're squaring it, would expand to y tilde x plus z plus w plus z colon w. That's how you say. When you talk of function, mathematical functions can be used in formulas. For example, log of y. So when you want to use some transformation, you can use a log, right? So natural base e, or you can also do some other transformations as seen on the screen. Now when you're looking at the regression models, you have some functionalities which we can use to see some of the outputs. So summary of any model will display you a host of things. Coefficients will list out the model parameters including the intercept and the slopes for the fitted models. The confident provides confidence interval for the model parameters, so by default it is the 95% confidence interval. The fitted provides you the list of predicted values by using the model on the same data on which you have created the model, right? And if you have to use it on a different set of data, you will have to use the predict function. The residuals list the residual values in a fitted model. The Anova expresses the Anova, which by default is not shown in R. So if you want to expand that, SPSS would give you the Anova table by default, but if you want to use that in R, you'll have to pass that model again into Anova. VCOV, that is V covariance, lists the covariance metrics for model parameters, and AIC prints the Akai key information criterion, which is a loss criterion. As the value keeps on going down, that indicates that the model is improving. The plot generates the diagnostic plots for evaluating the fit of the model, and the predict function is used for predicting the values for y given a set of x's. That's what we do. Right. Now the basic steps used to implement a regression model is specify the dependent and the independent variable, check for linearity in the data by using the correlation function or the variance inflation factor, also to check for some diagnostics like heteroscedasticity, check alternative approaches if variable are not linear. Say if it's not linear, then you have to check some other alternatives, estimate the model, test the fit of the model using the coefficient of variation, perform a joint hypothesis test on the coefficient, which is standard output in the regression table, perform hypothesis test on the individual regression coefficient, check for the violation of assumptions which are sure to happen, interpret the result, and use the final model for predictions.